All right. Lights, camera, action. Okay. Got all the AV set up. So I looked into doing some classes at school, and that's still a possibility. There are some pretty challenging constraints, though, with the room, the AV, and competing scheduling. We'll see what we can do. Be nice to meet in person, those who can. And of course, everything will also be available fully online for those who cannot. But hoping to make that possible. Not sure if that'll happen by next week for our visit with Jim McLaughlin, but I look forward to it. Hopefully it can happen. Okay, so we all have a lot on our plate that time of year. It's raining, shall we say, opportunities or call them challenges. But so I assigned more or less a lot of reading things for you guys to look at, and juggling a bunch of different classes at once, giving a test in another class today. And naturally, my largest class, it's raining, last minute requests. I need a special exception. Baby, caramba. So I'm trying to recall just what it was I assigned for you guys to read. There are a bunch of things. So as I said before, that there will be a lot of self-study reading, and I didn't really, we're not following lockstep in the chapters in the books, but there are topics, and I sent out some things I wanted folks to look over and get familiar with. So starting with that, I have a plan for today, what I'd like to cover today. And as always with these courses, I wish we had more time and I'd like to cover more. But before we launch into that, what questions do folks have? Shirley you must have questions. I do, and no need to call me Shirley. Sorry, airplane reference. Okay, shoot.
That Krieging handout, I wasn't able to open it. I don't know if anybody else had that like problem too.
That's a great thing to post on comments. Thanks, Matt. Did anyone else have any trouble with opening the Krieging comment, the little PDF? Anyone else try? Good for you, sir, for trying. I'll check on that. It's usually, I think it's pronounced Krieging. I'll check with my wife, but it's a method of spatially averaging, and it's not crucial that you look at that. But it's good to know that it exists and just have a feel for what it is. So last time we talked about isopleths and how you get those from scattered data points, involves Krieging typically. Anyone want to chime in who's had GIS? Do you guys use that in your course? Have you? Krieging?
I've used it, and definitely a refresher would be good. So I need to take a look at that. But I have a really good GIS book that goes into pretty intense depth about it that I can maybe post into the comments a little extra about it.
Sure, that's awesome, Hannah. And if you have something larger that I can, if you could send it to me, I can post it in the references for all to see, so they don't have to go to the Dropbox. Not sure. How can you guys post references? Does a comment have attachments? I don't think so. Anyway, notice on that. So yeah, you don't, good question, Matt. You don't need to dive in the weeds on that, but it's just good to know what it is and that it exists. And so a lot of this course and a lot of undergraduate education in general, you're essentially learning the kata, learning the dances, the forms, the vocabulary, and then the real learning begins. So especially with a hugely interdisciplinary class like this, what a essential point of what we learn is learning what we don't know, but knowing enough to know like what Krieging is used for, spatially averaging data to get isopleths, for instance, and that the GIS folks know about that. And that can be explored further with people who have expertise in that area. There's no need for us to try to become experts in all these things. It's not even possible, given the time, maybe several lifetimes and all. Good point, though. Thanks, sir. I'll follow up on that. And thank you, Ms. Hartman, for whatever you can post. And you guys can chat about this in comments. But was anyone else able to even open that attachment? Thought it was a PDF. I'll look at reposting it. Okay, and exposure measurements, industrial hygiene. Hopefully everyone read through that PowerPoint I sent out. Next week, we'll have a speaker whose background is IH, industrial hygiene. Did a master's in that. It sounds like it's pretty distinct from environmental toxicology, but it's not. It's really pretty much all in the same boat. It's just that it's a more restricted domain in the workplace. Now, for some people, a lot of people, in the workplace is an indoor environment, but not for everyone. There are forest firefighters, wildfire fighters, like Ms. Hartman, Hannah, and my wife fought wildfires, and I chased them with nephelometers on my back, and my wife trooped along, and we followed the Mendocino hotshots when they're here putting out a special fire at Kilauea, and those boys and girls are seriously fit. Respect, triple yeah, and so we traipsed around with our nephelometers, and so we were measuring suspended aerosols. That's all they see, their optical scattering, and that's what they see, whether it's smoke or ash. So we had two, one looked at below 1 micron in size and the other below 10 microns. So I'll just briefly jot a little something like that since we're on the topic. Okay, size, aerosols. So that's another note. What else in the reading did folks have questions on? Hopefully folks are diving into those, because there's no way to do this class unless you guys do some independent reading. No other questions. I'm going to keep adding to that list, and folks need to keep up on browsing those. Today I wanted to talk about tips on sampling and analysis that you might not read in books. Just discussed with size aerosols, I'm going to give you a general thumbnail sketch of aerosols. And on the test, you can expect to see things like we did as a gaming exercise. Here's an incinerator, and how do things get from the source to the near-sensitive receptor. So there's pathways, mass flux, advection diffusion, biovectors, ballistics, like that. We'll apply those tools. We've talked about sampling and analysis. I'm going to dive a little bit more into that. That's what I did for 20, 30 years as a career after a bachelor's and even before. You can make money doing analytic chemistry, indoors and outdoors. And then I wanted to talk today about, I have a PowerPoint on ideal versus real. And after that, we'll probably depart largely from our current focus has been a lot of physical, molecular kinds of things. And real quick soon, we need to dive into the organism and do some toxicology. But I just found yesterday a Scope, Importance, Knowledge, and Principles of Environmental Toxicology, a short little YouTube, I think, 6.5 minutes. I'll post it. And it agrees with what I've mentioned before, is that a lot of folks, maybe even they train specifically in etox or similar, and then they wind up on the job, and a lot of the training for toxicology, at least pure mechanistic toxicology, is molecular cellular events in the critter, in the organism. A lot of what environmental toxicologists wind up doing in their career, whether it's for the government or private industry, environmental impact statement, you may be writing it, you may be critiquing it, I've done both, is looking at the source, fate, and disposition of toxicants. where do the poisons come from? How do they move around, and how do they get into things we don't want them to get into? So that's why I've spent so much time on this, is that just judging from historical experience working in the field, especially in the HERE office at Department of Health, HEER, Hazard Evaluation Emergency Response. A lot of what we all did was involved with how toxicants get around, where they come from, where they go. So yeah, they probably have a web page which you could have a peek at just if you want, which I highly recommend folks do. So Hawaii Department of Health, sometimes is HDOH, and the HERE office for Has, Eval, and Emergency Response. So I worked there for some time and had the 40-hour HAZWOPER, hazardous waste operations, materials, resources and stuff. I did just semi-update my CV, which I reposted on there. Some of you are starting to ask me questions about your further adventures and trajectories, and I'm thrilled to help you out on that. If you have a squint at my background, it might help a little about that. Things I have background that could help you with. Okay, so no more questions on reading assignments.
Yeah, I have one more.
Thank you.
The TEDS, like gas sampling. You know your
Oh yeah,
your
I
the PDF.
spelled that wrong. Yeah, there's no E in there. It's TEDLAS. It's just one of many methods, and I can go on and on about analytic methods, but it stands for tunable diode laser absorption spectrometry. Tunable diode lasers are super cool. Diode laser absorb P or B, I don't know. Spectrometry.
Yeah, I wasn't able to open that one either. I don't know if it's
Oh,
my computer, but
I had an attachment. I didn't know I had an attachment.
no, I mean it was like the one that was uploaded into the I think it was number 2, test 2. Whatever. Let me see. Like the test 2 folder.
Okay. Check in.
I mean, I don't know. Like honestly, I don't know if it's my computer. I just got a new computer, but
All right.
when I try and open it, it says the file may be damaged.
Okay.
I haven't had any problems, Matt.
Oh, really?
Yeah.
Huh.
I don't know. I tried to open it on I tried to download it to my computer and like open it with Word. It's not opening.
Honestly, things are always funky with computers, so.
Yeah. Okay, here. So I'm sharing screen now, and let's see. Let me switch this over to protect the innocent, of course. Resources, test 2-ish. I've added some test 3-ish materials there for folks who want to preview into toxicology. Test 2 materials, off the cuff notes, one-dimensional transport, partial study guide readings. Maybe it was in readings. Okay, my machine asked to use Word, which, by the way, Word is available on the whole Microsoft Office. Here it is. Oh, that's Ted's guest sampling. It's available free to university students. So is this, am I on the track here, Matt? Krieging handout, PowerPoint. So this is going to be useful. This narrows down the field of view so you don't have to read like whole things I sent. These are lines from the talk I gave in Barcelona. PowerPoint shows work on diffusive samplers. I
Yeah,
don't.
I was able to open the readings for etox test, the document, but
Okay.
the PDF, your dissertation, your master's your the TDS or whatever document.
Okay, let me get rid of this. Is my other class test. Too many screens here. Fair games, one dimensional, partial two. Sorry, is it one of these?
Let me see on my computer.
Oh, well, maybe hit me up after with that,
Yeah.
and
Okay.
I'll try to repost that in a couple different formats.
Okay. Sounds good.
Right. But yeah, these are useful acronyms. I hope everyone definitely went through and read those. So they're fair game for tests. There are close to 200 of these. This is super short list. Trust me, there are more. So these are fair game. Lowest observable exposure limit or level. I think it's level, maybe it's limit. Observed effect. Observed effect may not be adverse, so they put the A in here for adverse. Okay, so permissible remediation goals for Superfund sites for soil. Lethal dose 50%, and down here these are industrial hygiene type terms. So first responders like to know this one. This is immediately dangerous to life and health. So anyway, there's a lot of alphabet soup in there. Oh, come on. Get this out of there. All right. Okay. So, and there are also, I think there was somewhere else I had things posted of use in the PowerPoint shows. So most of those I think are, today we're going to cover this one, ideal versus real. The others we've already talked on. The IH, industrial hygiene, I signed as reading. The Barcelona talk, I gave you a breakdown about, so you wouldn't have to read it all. I pointed out certain things. Here's the Krieging handout. Just open it as a PDF. You might have to get a newer version of Adobe there, Matt. That might help you out. And again, don't worry about the weeds on this. Just get a broad brush strokes. You could even look it up, short YouTubes on it. Wiki throws you in the deep end, but anyway, here it is. So yeah, it seems to open. Have a peek at that. Ideal versus real. So I'm going to open that up and we'll look at it in just a bit. PowerPoint, come on there. Okay, yeah, and Jim McLaughlin just sent me something to open. Why is this not opening? Okay, gosh, the screen frame is blocking my ability to open downloads. It should be, just downloaded it. Arg, things should work. This is so frustrating. Why don't things just bleep and work, right? Okay. Actions, we'll try this out. Open in new window. There we go. Come on now. Really? Okay, I'll just find it in my files. So if people have trouble opening these, please post it on the Commons, and others might help you. And if it's a junk or corrupted file, I'll gladly go in there and fix it. Add another one there. Okay, talks, PowerPoints, global hazards, ideal versus real. Okay, but before we get to that, down boy, I wanted to touch up on some basics that we'll need to know going in. So we've talked about exposure and how to measure it. Okay. Exposure's outside the animal. And does anyone remind me what are the basic units of exposure? There are two fundamental units that we measure. Help me out. Concentration, of course, and what? Exposure is in units of concentration times time. Does anyone remember an example? Like ppm times hours. And last time we looked at integrating the area under the curve if we had like concentration and time like this. And we looked at something that might be like a rush hour traffic signature. We might have morning versus evening. So we could just get the area under the curve, AUC, area under the curve, which is, for those who've had calculus, just the integral from T1 to T2 of concentration as a function of time, dt. So it's just the area under the curve. It's like in the morning, in the midnight, very little, and then, so we've been through this, it's in previous films, but, so that could be, it could be like, they might have to say like 24-hour average, or 1 year average, or it might be an 8-hour average. Oops, I can spell average. And then in the IH, in the industrial hygiene thing, they talked about time weighted average. So if you had like an 8-hour work shift and then the levels of something were high at one point and low at another, you might have like rolling 1 hours, or you'd have like this time bin times the time. So there's this average concentration times this time. So C1 times T1 plus, and then you'd have another time window and another C2 times T2. So this is in the industrial hygiene thing you all have read, and all divided by the sum of the times, like 8 hours in this case. Okay, that's time weighted average. So there are a bunch of different ways to look at exposure. These are just talking about data representations, right? And there's also the peak, right? Peak exposure. And so I brought up before, this is review, when would peak exposures be important as opposed to just, say, a 24 or yearly average? So for a really slow acting cumulative toxicant like metallic mercury, you really mostly care about the yearly exposure. But for certain toxicants, the peak values are important. And that's due to the nature of how the poison interacts with the biology. Does anyone remember there? Just in general terms. When are peak exposures, when/why are peak exposures key or important? Heavens. I spent some time on this. Gave an example, sulfur dioxide. And basically the take-home message is that they are reactive toxicants. So by reactive, they can be just react with something right now. Reactive means they want to react. So sulfur oxides, nitrogen oxides, carbon oxides, they react with water to make gases. Collectively, they're called acid gases. So reactive toxics react with tissue, and they can do it fast or quickly. And the tissue has limited buffering, or let's just say ability to handle / tolerate reactive chemicals. Okay, so acid gases like SO2, SO3, NO2, these are oxides so collectively, by the way, they collectively call these SOX, where for sulfur it can be 2 or 3, NOx, where it could be, the X could be 1 or 2. So that's just a little side note, that's not crucial. Acid gases, it sort of sounds reactive, right? Acid, do you ever pour acid on your skin? Do you like wait until sometime the next week to wash it off? No. Why do you wash your hands right away when you get acid on them? Because your tissue has limited ability to handle or tolerate it, and they react, what was the word I used, fast or quickly or rapidly, or you get the picture, on a short time scale. So if you get just a little bit of acid, like dilute acid or something, low concentration, remember here we're plotting concentration against time. So if you have a high concentration of acid gas in your lungs, acid on your skin, then you might need to notice that, deal with it, or control it. And so in those cases, the peak values are of greater value than the average under the curve. Okay? I'm going to assume that people have the gist of that, the flavor. That's the second time I've gone over that. So review that, discuss it amongst yourselves. So ways to sample or measure exposure. We covered some basics. Anyone remember? You can have a whole career just on this alone. So the very simplest was a parcel of the matrix, limited in time and space. They are glibly called grab samples, right? So that's like a parcel of air or water or soil. But of course, as I said last time, again, this is review, which we don't have time for, limited to one place, limited in space and time. S&T, one place, one time. Clear? So it's just a grab. You're just grabbing a parcel, a liter of water, a bag of air. All right? Got it? Good.
Yes.
And then we have averaging, like integrative samplers, averaging, like integrative samplers or monitors. So what's the difference between a sampler and a monitor? A sample just grabs some of the material you want to analyze. A monitor measures it. So sampler, just like it sounds, it samples, and monitor takes some of it in and measures it. Okay, so we might have a sampler or a monitor that might give us, say, an 8-hour average or a 24-hour average. Where am I going with this? Or 1 year average. All right, you get the idea, right? That's the idea. It's an average. So what that doesn't see is the peaks. That was the whole point of my master's thesis, was one very popular member of this group are diffusively controlled, diffusive samplers. Is a classic example of averaging or integrative samplers. And with those, they're sampling, and then you grab the stuff that's collected, take it to the lab and analyze it in the lab. Okay, so those are two simple ones. There's also, you can also have, they have this evacuated stainless steel ball with a little, here's the little engineering symbol for a valve here. And there's an opening there. And this is stainless steel hollow ball. It's about the size of like a basketball. They're pretty pricey. They're electropolished passivated 316 stainless steel, which you don't need to know. They're called Summa canisters. And they're evacuated or vacuum. Evacuated. Vacuum at time equals 0. And then you can, the valves, and they have little filters, little stainless steel sintered metal, they call it a frit. It's just a filter so that you don't get bugs in there and whatnot. And you can get Summa canisters that suck air. So basically they suck air until they reach atmospheric pressure. And you can get a 1 hour, how do you spell hour? 1 hour, you can get an 8-hour canister, you can get a 24-hour canister. Okay, and you open it up and they just suck air for that long and then they're full. And you send them off to a lab for analysis. It's, you don't need to know the deets. 316 stainless, just for the geeks, stainless steel. It's an alloy that's the least chemically reactive, and treat it further, electro polish. I don't necessarily want you to memorize these details here. My purpose in showing them is that they exist, and there's a term called passivated, where they etch out the steel has different little portions at a microscopic scale, so they'll use like dilute nitric acid to etch out the ferrous, more reactive parts. Again, details you don't need to know. I'm just pointing out they exist. What do you need to know? That you can get a hollow ball of steel with a valve on it. You open the valve and it can suck air for an hour, 8 hours, 24 hours, and like that. So when you analyze that, what time period are you getting? It's not an instant of time. It is an average over however long it was open. Clear?
Yes.
Great. Moving on. So there's a couple of those. Okay. And just taking a peek in the weeds, like in my thesis, will it helps spell out a little bit of some of the meets and bounds, like in surveying the edges of the property, and you can dive into the details too. And boy, there's just so many things. There are bubblers, there are all kinds of ways to do this. Yeah, there's, we'll just jump to real-time monitors. So in real time, they give concentration versus time. Now, for all of these methods, all methods of sampling plus analysis, which may be in one analysis. So a monitor does both sampling and analysis. We just looked at several methods that did only sampling. And then later you do analysis separately in the lab. But all of these methods have limits, and limits in two things: time resolution. So what's that mean? Time resolution. So if it's an 8-hour average, you cannot resolve anything finer than 8 hours, right? So time resolution is averaging period, or the finest delta T that can be detected or seen, measured. What do I mean by delta T? Change in time. So that might be hours, or for a so-called real-time monitor, even them, they might not get a value every second. So I used one, nephelometers. Maybe it had, say, 10-second averages presented, and this is user selectable software presented. That's in the data saved and or screen display. And these might be different. You know, you might have the screen display might be like 10 seconds, and then the data saved might be 1 minute rolling average. So we talked about that briefly last time. I'll just show us a little reminder. Okay, and I did take Matt's suggestion and scanned last time's notes and posted them. I hope you all got those, and I'll do the same with this, I guess, although kind of a scribble fest, but okay. So basically we're talking about things that give us a picture over the course of like an hour, 8 hours, 24 hours, something like that. Now these so-called real-time monitors can see, many of them second by second, but they don't necessarily trust each second. Oh, I'm sorry, limits. There's one more fundamental limit. Okay, they have limits in time resolution, and they have limits in how small a measure they can see. So this has got a variety of names. LOD, that's limit of detection, lim of detection, or it might be minimum concentration level, or there's a whole bunch of things like this. It might be lowest quantifiable level. There's a whole bunch of ad nauseum. But what do they mean? What do they physically mean? Here, we're looking at the limits of time. What are our two fundamental parameters we're looking at when we use these things? We're looking at concentration. That's important in exposure, right? And time. So if you go into a room and it's 15 parts per million formaldehyde and you breathe for 10 seconds, you have a different exposure than someone else that goes in the same room and breathes for an hour. So the time resolution is important. So this is concentration. So all of these LOD, there's a whole bunch of names, lower detectable limit. It just goes on, but they're basically the minimum concentration reliably determined. Reliably. So here's the thing. If you talk to a sales representative and ask, how low will your instrument go? The sales representatives have some pretty expensive, pricey gear. They don't understand the fundamental science, and they'll say, oh, this instrument measures from 0 to 10 parts per million. Well, nothing can measure, very, very, very few things can detect the presence of one molecule or one atom. So minimum concentration, it's how low it can reliably see. The most general term for lowest detectable limit which somebody might call LDL, again, they have a whole bunch of acronyms, is where signal over noise is the ratio, or S to N is greater than 2. Okay, so let me give you a little picture there of that. So let's say I've got concentration and time, and here's my instrument reading. Okay, so maybe I get a little, so there's always some kind of noise where it's uncontrolled variation. There are a whole bunch of reasons for that, physically and chemically, thermal variation, sensor, responding to different things and stuff. And then signal is, let's, for lack of a better word, call it real measure of analyte. So we have sort of a noise envelope, and there's a bunch of math and statistics, and there's a whole bunch of different ways to do this. So we have a noise sort of range or envelope.
Will you move the screen?
Oh, thanks so much. Okay, thank you, ma'am. Okay, so this little peak peeks up its head, and we can say that looks like barely, this looks like about 2 times the noise, this little peak here. So we said limit of detection typically signal over noise greater than 2. Okay, so this little peak here stands up about twice as big as the noise envelope. 2 times the noise. So we could say, maybe we saw something. What about this little peaklet over here? To my eyeballs, and again, this is done with numbers and math and statistics, but just eyeballing it is actually not bad. Does that look twice as tall as a noise envelope? I'm going to say, nah, that's dubious. So you see, so you can't really say you detected that. So what is this in terms of concentration above background, above baseline? So how much is that? Is that like 1 or 1 ppm or 3 ppm? What is that? So what is this value? How low can it detect? All right, so some instruments, some real-time monitors, they can see down to, like for environmental, like outdoor ambient. Now this is true in water, air, soil. So environmentally, we often aim or need to measure in parts per billion range. Okay, so that's often of interest for environmental ambient, air, water, soil, to be able to see to the parts per billion. That's 10 to the minus 9. Okay? In occupational or industrial hygiene, it's typically ppm or even percent. So you notice how that these IH, industrial hygiene type monitors, they are how sensitive compared to what we often need in environmental toxicology. Well, ppb is different than ppm by a factor of, what's the factor of between 1 million and 1 billion? That's a factor of 1,000. So these are 1,000 times less sensitive. Percent would be 10,000 times less sensitive. Okay, so if you look at some of the work I did for atrazine in the streams, I hope you've done some of the reading I asked, we were seeing into the low and even below 1-digit part per billion of atrazine in the streams. So that's much, much different than ppm level. One of my greatest frustrations moving to Hilo from Manoa, when I was teaching at Manoa, we had a whole lab all set up and dedicated with the gear operational running and stuff that was operating in the parts per billion region for organics, for metals, you name it, we had it. Air, water, soil, it was a lab for the School of Public Health. I moved to Hilo, I had to carve one of those labs out of the basalt of the Big Island, given, I was given a pile of money, 100, 200,000 a year for almost 10 years. I'd get a lab like that set up, and then some dean or other says, well, we decided you've got to move your lab. You what? It's like having a professional kitchen times 5 and you have to move it, not once, not twice, but 6 times in the course of like 7 or 8 years. I just gave up. I just said, come on, it's ridiculous. Anyway, so these types of instruments like firefighters or emergency responders or industrial hygienists are not going to tell you what you need to know in the parts per billion range. They're not, because they're 1,000 times not sensitive enough. The sales rep will see, you ask them, how low does it go? Well, it sees down to 0. No, you don't understand chemistry or physics anyway. So signal to noise of 2. So typical limit is signal to noise, or SN, or S/N, greater than or equal to 2. So that's sort of the standard definition. There's a whole bunch of others. I guess I spent way too much time on that. So what have we covered? We looked at, not going to even have time for the main thing I wanted to do today. So we've got grab samples, right? And you could discuss their limitations. And integrative, or averaging, sample plus analysis. We've got real-time monitors. And then there's one in industrial hygiene called personal monitoring. So the thing about these real-time monitors, especially for environmental, ppb level, that we need for environmental, is they typically are more than $5,000 or $10,000. Some might be $40,000 or $50,000 for these instruments. They're probably getting cheaper. And they can measure, where can they measure? Typically, TYP, at one point in space. That means one place, yeah? So they might have lovely time resolution. So real-time monitors have limits of time resolution and concentration resolution. Resolution, what can they tell the difference between? In astronomy, they talk about resolution like, or your eye doctor, you say, is this 2 spots or 1 spot? You know, and maybe the planets are sort of overlapping, and, you know, can you tell them apart clearly? You know, resolution. So in astronomy, these are resolved. In chromatography, you might have a signal like this, and you might have a lovely peak, and then you might have a couple of more peaks. Well, this peak is said to be baseline resolution. It starts and ends up at the base. These twin peaks are not baseline resolved, and you got to use some fancy math and extrapolation and stuff like that. So we've got grab samples, integrative samples, real-time monitors, and personal monitors. So the personal monitors, they're typically not very sensitive, typically ppm or percent. But the thing about space, where the fancy real-time monitors see to the parts per billion, what's the limitation of the fancy real-time monitors? 1 point in space. Where do the personal monitors go? So not great concentration resolution or detection, but great in terms of representative of where the person is. Person's exposure. Okay, so if we have a city, let's say this is Phoenix, And we've got a real-time monitor for, let's say, NO2. We've got one here, we've got one here, we've got one here. And this might be on the scale of, let's say, 30, 40 miles. So you might have 3 monitors in the city of Phoenix. And then you get estimates and you might use some kriging to get some. So let's say Johnny or Susie in Phoenix here, they wander around, they move in time and space, and they're not in one place. So how do you get the estimate of how much this person breathed? Because they're moving, you see, they move. Over time, they move. So that's a limitation if you have only monitors at one place. You might have a few places, and you might smooth the data by kriging or some method to get. And then you might have a time activity budget. So that's another thing, but time activity budget. But basically, personal monitors they follow the person. They are on the body. Got that? You wear them. So where the person goes, the monitor goes. Follow? And if it's an aerial toxicant, you might have the monitoring tube might be in the backpack or a little badge or something, but it might be near the breathing zone. That's the part of the body where air goes in. So I'm always curious, people talk about mosquito attraction and CO2. They're attracted to CO2. Well, last I checked, I've got more hot air coming out of my mouth than out of my ankles. And the mosquitoes zoom in my ankles. Well, so there's something more than just the CO2 thing there. We'll talk about that later. So I'll just briefly introduce what I wanted to talk about mainly today and leave you to read on it and ask questions. And that's the difference between real and ideal. So we're taught in Gen Chem and most of even analytical, a lot of times we're taught, and the laws we learn, like Henry's law, KOW, those are in what are called ideal conditions. So, oh, come on now, I opened this puppy, here it is. So the assumption, often unspoken, and I'm trying to train you guys up to look for those unspoken assumptions, is that everything's hunky-dory and ideal, but it's not. So most of what we learned in Gen Chem, let's see, can I make that bigger without going to full screen? Yeah, good. And I'll slide that over here. Okay, so most of the laws we learn, Henry's law, KOW, they apply to ideal conditions, at equilibrium. But usually in the real world, it's not. So I want you to be at least on the lookout. So I'll just blast through this and, we can cover it again, I hope, maybe, but you should read through it with this in mind. So in a real chemical matrix, a typical chemical matrix in the lab, ideally, where molecules play, it's homogeneous, like pure water. It's the same throughout, same throughout, generated at all scales. Isotropic, the same in all directions. One phase, it's not part solid and part liquid, it's all liquid or all solid. An ideal gas or a dilute solution where low interactions or at least similar, I wrote this on one of my notes, solute, gas, solvent, the intermolecular forces are all similar. You can look up ideal gas, ideal solution. Non-binding matrix, it doesn't grab onto the solute. The solvent doesn't grab it. So there are examples. Pure water, dilute, aqueous solutions, they're pretty close to ideal and real, or pretty close to each other. Dry air. Okay, but seawater, urine, blood, bone, rock, soil, those are more complicated, not ideal. In real, so this is just a repeat of what we just went through. Real's not homogeneous, and it might vary with scale of size and time. Not the same in all directions, like a book. I showed a book, I could pour water through it one way better than another. It might have more than one phase, solid, liquid, gas, and plasma is coming into play. Even in biological domains, I just saw an interesting article on that and talked to this guy at the medical school where I trained, Stuart Hameroff. Anyway, interesting about non-ideal behavior, complexation. We're going to come back to that. Soil, tissue, lakes, the sea. Okay, come on, move along. Move along. Okay, so water, pretty ideal. A box of air. So within that box, it's probably fairly ideal. By the way, here's a classic example of this person. She's measuring mass flux of methane out of the tundra. Now, how's mass flux different than concentration? Concentration is at a moment of time. Flux has time. Where? In the denominator. So she has to have flow to constantly flush the space with fresh air to find out how much new methane is fluxing from below this surface into the box. You see, mass flux is not identical to concentration. All right, so here's some not and, prefix and, Greek meaning not, iso meaning same, not the same, trope, turning. So you turn in different directions. If you could dive into this rock like buckaroo banzai or rain infiltrating, it's not the same. Or in leaf litter, transport across the layers, you might get better water flow, worm flow, or stuff than through the layers. Geology, aquifers, soils, they're not the same in all directions at all scales. These are real matrices, you see that. Groundwater plumes occur in real matrices. And so you've heard of scalars like temperature or pressure. Then a vector adds like a direction, another bit of information. And then there's a thing called tensors, which I'll briefly get into. That's in the realm of, don't worry about it, but it's just, it gets a little chewier is all. I can give you an example of a tensor, but limnology, lakes have layers. Oh yeah, there's this Kivu, which is like Lake Neos, but 2,000 times bigger. So looking here, just glance at limnology, write that down, look it up, just wiki that puppy. That's, lakes have complicated things. So do oceans. I notice some have had physical oceanography. There are different thermohaloclines. We talked about the boundary layer in the atmosphere last time. So, okay, Lake Kivu is remarkable, and there's just a real amazing full-length video on that where politics and everything else come into play. It turns out there's methane in addition to the CO2. Anyway, so here's a side view, noticing depth. So when you see a graph of some kind, please read the axes, and shame on whoever allows their being published without labeling their axes. Here I see depth. Now that's nice. We know these numbers refer to depth in the water. We even know what lake. But can anyone tell me the units here? Is this centimeters? Is it inches? Is it meters? Is it kilometers? Being a lake, it's probably not kilometers. But you see, bad dog, no biscuit. You must label your axes, because in science, we do two things. Show what we did and what we saw or found. Isoplus of turbidity, the ability to pass or scatter light. And you notice it's not the same everywhere. And noticing that across the bottom here, we have months of the year. It changes seasonally. So a lot of lakes do what's called inversion. They do a seasonal inversion. And that's typical of temperate lakes, where seasons change temperature. It's not so typical in tropical lakes. Okay, soil from a chemical point of view. It might be different at different layers. When Gary, Sue, and I looked at landfill fires, and Hawaii has a bunch of them, it's different at different depths. So where we sample and where they inject the liquid CO2 and where things go and come from and how they move. There are gases that move through soils, water, non-water solutions like solvents. Okay, here's the atmosphere. It has layers. This is just a textbook picture. Most of what we're interested in is down here in the troposphere, and that, as I mentioned, has things like a boundary layer, inversion layer. And here's a side view of a weather front. This looks like a cold front where cold polar air is coming in. It's colder, it's more dense, and it works its way down under the warmer air, as opposed to a cold front where the cold air, cold and warm fronts, they have different interfaces, a systems term, interfaces, mixing. There's a lot of interesting stuff here. So this is a side view, and it's dynamic over time. Here's a plume, one of the things that I spent some time on. Here's some aerial pictures of plumes. And you might have an isopleth for this, but what do we know an isopleth in 2 words? They are dynamic in the real world. They represent dynamic events, typically, not always, but they can be dynamic, meaning they change with time. And the other thing is they're statistical averages. They're probabilistic. They're not hard, solid lines. It says it's exactly this value on one side of the line and the other. The lines are usually 50% between the values. It's the same with the Pourbet diagrams. Q equals VA, concentration is Q divided, anyway. So fluxes, so here's like we drew the incinerator plume. This would be a point source, and stuff can leave the plume, gases, solids like aerosols. I was gonna draw a picture of aerosols. Stuff might get out of the building and go through the ground and move by groundwater. It can get rained out of the cloud in what is called wet deposition. It can also settle out in what's called dry deposition, meaning it doesn't require rain. Then it can get into crops, into water, into ecosystems, into food, into people. Pathways, folks, think pathways. Be able to draw a connect the dots pathway. My wife says, somebody said, what we need is someone to connect the dots. Well, generally what we need is someone to identify the dots. Any fool can connect dots, but not necessarily in the right way. But identifying the dots. What are the things of interest where this is going? So pathways, cradle to source to receptor. Okay, representative of what? Peak exposures, hourly, yearly, exposures to whom? Aquatic biota, humans, forests, tortoises, sampling biases, systematic and incidental, analytic sensitivity, limit of detection, lower detectable limit, less than, we talked about that. Analytical interferences. So let's say we're measuring for cadmium with ICP, inductively coupled plasma, or like X-ray fluorescence. There might be things, other metals that are positive interferences, meaning if we think we're just measuring cadmium and we have some other metal there, we might get a signal even though it's not cadmium. That would be a positive interference, giving us a bit of a false positive added to our signal. We can also have negative interferences, things present in the mix that's non-ideal, that we might be measuring for one analyte, one chemical, and something else in there might mask it or complex it or bind it or make it unavailable for reporting, that we cannot detect it. So we can have positive and negative interferences in our signals. And similarly as the test overall, we can get false negatives and positives. Finite, meaning non-zero. So this is an issue with COVID testing. It was an issue with some people on pain meds. Their doctors test to see if the pain meds are in their blood. And I knew a physician who, they had some tests that came up negative, and they accused the patient, was supposedly taking the pain med. Well, you're not taking it, so you must be hoarding it, so you must be selling it, so you must be a drug dealer. Well, that's an awful heck of a lot of assumptions based on a negative test report. And I pointed out to the physician and the clinic that, careful, tests, I did this for a living, I evaluated tests. None of them are perfect. They have false negatives and false positives. Toxicology, pharmacology, we used to joke about, yeah, poppy seeds can give false positives for opiate use. Papaver somniferae, a poppy plant, is where opium comes from, and heroin. And the seeds can give false positives, or at least could on some. So those exist in tests. Physicians should know this, but they're very black and white. They use science, but they don't understand. They're actually not really well trained in science. They have to deal with a patient in public health or medicine. You don't have the luxury of getting a whole bunch of things and getting more data. You have to make a decision. So look for these kinds of things in science literature, news reports, and whatnot, okay? Concentration over time, let's see, I got about a minute left. So here's a snapshot of what is believed to be anthropogenic ozone. So this is not ozone layer stuff, that's in the stratosphere, which is way, way, way high. This is down here where people breathe, in the very, very, very lowest part of the troposphere. Most people aren't much taller than 2 meters. Some elevations are above sea level, but none of them are anywhere near the stratosphere. So these are ozone in the troposphere. Turns out, in concentration isopleths, they change over time. Okay, and looking at sulfate, non-sea salt sulfate. So sea salt has sulfate in it. So how can you subtract out the sulfate due to sea salt in aerosols? We might come back to that. This is Fukushima Daiichi looking at the isopleths of nuclear stuff. Speciation, so just briefly, mercury changes form from elemental mercury to an ion, mercury 2. And methyl mercury, or dimethyl mercury, very, very toxic, worse. So things change as they move. Where do you measure? What's your question? Do you measure in the apex predator? Well, that might be a quick snapshot of the mercury in the ecosystem. You could measure in the sediments down here, or benthic detrivores, things benthic bottom, detrivores, things that eat the gunk on the bottom. You could measure in the pore water between, you could measure in the water column, you could measure in the plankton, a lot of places you could measure sources from industry, you could measure mass flux into the air. What do you measure depends on what your question is. But there are a lot of places this can take you. And I used to get paid to go in the Sea of Cortez to measure trace gases and up in the mountains of Arizona and all of that, great fun. So just real quick, like a bunny, while I'm over time asking questions, but particle number, switch camera. So I just wanted to give an idea about aerosols. Overview. So this is a very crude curve. This is about 1.0 micro, that's a prefix you should know, 10 to the minus 6 of a meter. And this is about 10 microns, micrometers. And there's this fine mode, less than, so this is less than 1 micrometer. And this is the coarse, or they call it accumulation mode. So this is just a sort of a natural distribution of size of aerosols. And we were taught that if it's greater than 10 micrometers, it falls out of the air in quiet air. So They say it's not an aerosol, but as we saw on the picture, can still be airborne, like in sandstorms, like on the picture. But these also will settle in quiet air, quiescent air, class F stability and stuff. So especially from this fraction, we would expect to get dry deposition, meaning it falls out of the air. These guys, these make it into the deep lungs. So if the regulations are a tension between science, toxicology, and industry. Industry wants to put as much stuff in the air as possible. All the regulations used to be on everything below this line, just integrate across all of it. They called that particulate matter 10 microns and smaller, PM10. Recently, so that's everything here. Recently, they drew the line at 2.5 microns, and it was a struggle between science and industry. So most of the regulation now for aerosols is 2.5 microns and smaller. So that's smaller or equal to 2.5 micrometers. Now that's not necessarily the best for toxicology or public health concerns, but it was fought like tooth and nail in court by industrial lobbyists, the coal industry versus like the Lung Association, which I was on the board of directors for 10 years. So it's a tussle. This is now what is regulated. A lot of historic data are this. Now, size resolution is not given in these data. It's just everything smaller than 10 micrometers, which means most of the stuff in the air. So sea salt, road dust, pollen, they're all in this stuff. Smoke, a lot of finer things are down in here, and these can be more damaging. Anyway, that's a lot of information in one go. But it just goes to show it's not as completely simple as we might be led to believe. But so just kind of giving you some cautions, and some of the main take-home things are we got grab sampling, time average or integrative sampling, real-time monitors, personal monitors. Okay, you can look for gases, you can look for aerosols, that's in the air. You can measure stuff in the water, dissolved, suspended. We'll get later into chelated and colloidal. And then there's soil, which is, wow. So what at least I am hoping for all of us is that when we see things reported in the literature, we start to ask a few questions. And don't necessarily believe, everything you see. And, if you see an isopleth that says, oh, you're here, it shows right here, you're just on the safe side of the line. Those lines are averages, and they move. Generally, they're dynamic. Even in the Porbet diagrams, you see a line between one species and another. That line represents it's 50% one species and 50% the other. It doesn't mean it's suddenly they all change identity. I'm going to be an ion today. No, it's a gradation. It's a dynamic equilibrium. Okay. But you know a lot. You know more than you think you do. So hit me up with questions and shoot me messages if you need some more explanation. I'll happy to meet privately with folks. And this is posted, and go through it again and drum up some questions about it, and I will be happy to answer them. I'm going to stop recording.